Okay, we're going to spend a little time on naming ionic compounds first, and then I'm going to show you some molecular compounds. So this is naming rules, not naming rules. It does kind of rule, but these are the rules for naming. Um, so when I think some of the ways of doing this are really important to construct this knowledge in your head. And so I'm gonna use this method that I have been using for years that I saw someone else do, and I thought it was a really great idea. But I want you to work through these things with me here. But I want you to look at so I'm going to give you the naming rules in the end. You don't have to copy these down. I'll post them both for ionic compounds and molecular compounds, the ones I want you to know. We'll do some practice, but I want you to look at these names here. So these are ionic compounds. So remember, I told you come up with the fact that it's an ionic compound, knowing if there's a metal, you know that this is an ionic compound. So these are ions. Okay, they're not sharing electrons, they're ions. Same with this. Calcium's a metal. This is an ionic compound. This is an ion and an anion and a cation. Okay, so if you look at these, if you pause the video and see, so based on the names that I gave you in the previous lecture, what are the general rules that you see? Okay. Now, so hopefully you pause the video, you tried to write down 3 rules. You can see, I'm going to give them to you here now. You can see that the cation is always named before the anion. So sodium ion, which is +1, the chloride ion, which is -1, is written second. So cation name before the anion always. So if you saw a formula, and you know that the first thing written is always the cation. So calcium's the cation, nitrogen's the anion, nitride. The anion ending is dropped and "ide" is added, and we know that's true for all monatomics. These are monatomics. Even though there's a 2 there, there's a reason there is. And no prefixes are used. Numbers of the ions can be determined by the charge. So I'm going to show you these on the other page. So if I wrote down something like calcium nitride, well, you would know that this is an ionic compound because this is a metal. So we can look at the periodic table and know that that's a +2 because we memorized that. It's in group 2. And nitrogen, we know when it's an ion, it's always -3 when it's a monatomic or ends with "ide." Now, this isn't nitrate or ite or any of those others. So now, when we write these down, we need to make them so they're neutral and the lowest ratio possible. So remember, ionic compounds are really empirical formulas, so we have to make them neutral and lowest possible subscripts. So that means the empirical formula. And I told you we call that formula unit with ionic compounds. So if you think, how can I make these neutral? Well, you have to come up with a common denominator. This is a little trickier. We also had in that, and I'll write that down here in a minute, but we also had sodium chloride. And when we do that, the sodium was +1, the chloride was -1. We can get that from the periodic table. And these together cancel each other out, so we just write them as NaCl. Okay, that's easy. And if we had something like barium oxide, that too would be easy because barium's +2, oxygen is -2. We sandwich them together, BaO, because they cancel each other out. But these don't. So one way people oftentimes do that is they crisscross these down. They bring the 3 down to here and the 2 down to here. And that works most of the time. It would work here. It wouldn't work for the barium oxide because you would have 2 and 2, and that's not the lowest subscript. So you just squeeze them together. But in this case, in a sense, you're coming with a common denominator, which is 6. So you need 3 of these to get 6 plus, and then you only need 2 of these to get -6. So that's how you get the Ca3N2. So they have to be written in a neutral way for that to work. Okay? So I'll give you a bunch of practice sheets to do these, but that's an example of a correct ionic compound. So when someone says calcium nitride, you should know as a chemistry student that that's Ca3N2. Okay? Now, let's do another one. Let's try another set with the missing rules. So we know the rules for general ionic compounds. Now, here is something to think about when they have polyatomic ions. So notice this one is ammonium dihydrogen phosphate. Okay, that's actually an ion in and of its own, dihydrogen phosphate. And you know phosphates, PO4 minus 3, and then there's two hydrogens that really give it two more pluses. And so H2PO4 is a minus 1 ion, and ammonium is a plus 1 ion. You just have to memorize polyatomic ions. Aluminum sulfate, you'd go, well, how would I get that? You just have to memorize it. And that's my rule. It's kind of a crummy rule, but it is that polyatomic ions have unique names and you just have to memorize them. But you treat them just like these other ones. So if we had something like, let's say sodium sulfate, well, we'd know sodium's plus 1 from the periodic table. It's a monatomic. You just had to memorize that this is SO4 minus 2. Now, to make this neutral, you can either crisscross, and that works in this case. So Na2SO4 is sodium phosphate. Okay, you notice we never say disodium phosphate. We don't, because we get the charges and the ratios through our foreknowledge of ionic compounds. Okay, now I'll show you that phosphate, a lot of these polyatomic ions that have a charge that's like -2, 3, or 4, you can put a hydrogen on them and think of a hydrogen as a plus 1. And so you could add one of these and then it's PO4 minus 2 with an H in front of it. That's hydrogen phosphate. This is phosphate ion. This is hydrogen phosphate ion. And then you could add one more if you wanted and have H2PO4. And since these are plus 1s, when you're adding them, they change the charge as well. So this would be minus 1 now because the plus 1 comes in with this. Kind of like that. And so this is dihydrogen phosphate. Okay, that's where those names come from. So you got to be able to keep that in mind when you see these compounds. So in fact, if you saw aluminum sulfate, like what that was on that other problem, well, you know aluminum from the periodic table is plus 3. It's a main group element. I didn't give it to you, but it always is a plus 3. And sulfate is SO4 minus 2. So you would have to crisscross Al2SO4. And if you need 3 of these, you have to put it in a parentheses and a 3, because it would be weird if you put SO4 3, then people would think it as SO43, which isn't right. So you have to put brackets around that when you see that. Okay? Now, one more set of rules for ionic compounds, and this has to do with transition metals. So remember, on the periodic table, when we see a transition metal, we know that these charges of these transition metals, we can't really figure out. So I'm talking transition metals, even these lanthanides and actinides, these inner transition metals, and then even these over here, these metals that are in the main group, these are all sort of an unknown. We just don't know what their charge can be, because they can have a different charge. They don't have to just be one set. So if you look at this, the Roman numeral is given in the problem, in the name, so that you know which charge they are. So my last rule for transition metals is the charge on the transition metal must be given. So you would call this copper 2. That's how we say that, copper 2 chloride. And that's different than copper 1 chloride, which I'll draw on my paper here. So if you saw copper 2 chloride versus copper 1 chloride, and remember that's a Roman numeral, okay? Copper in this case is +2, chloride's always -1. In this case, it's copper is +1 and chloride's -1. So when you bring these together, this is CuCl2 and this is just CuCl. Okay, so because the reader of that name wouldn't know the charge on the transition metal, it has to be given in this problem. So that's red, copper 2 chloride or copper 1 chloride. So anything on that periodic table in the middle here, then the charge actually has to be given in the problem. Okay, so that's a little trickier, but you just have to spend some time memorizing that. Okay, now I'm going to look over the rules here for, those are ionic compounds. You have some worksheets that I want you to do, practice them, but I'm going to put in there also some rules around simple molecular compounds. Okay, we call them binary. Binary means two elements in the compound. So when we think of, when we're going to solve these, these don't have charges, and this is the number one thing that should lock your brain up when you're doing these. So if you saw something like CO2, and if I see above there, I'm like, well, a copper, or let me do a different one. Let's say I saw something like SO2. If I see you writing like, oh, sulfur's -2 and oxygen's -2, I know that you know that that's not a molecular compound. Remember, these are nonmetals, so they're not ionic. So what you have to do is, we can't talk about them or figure out the ratios based on the charges. So we have to use the name to figure them out. So for instance, carbon and oxygen, 2 oxygens versus carbon and 1 oxygen, you probably know this is carbon dioxide, and this is carbon monoxide. Okay, so when you're looking for binary compounds are 2 nonmetals. Okay, simple molecular compounds. Remember, molecular compounds are nonmetals and nonmetals. These are the rules. So I gave you a definition, contain 2 types of elements, nonmetals, covalently bonded to other nonmetals. You name them in order of their group number. So that means that you go like carbon before oxygen or nitrogen before oxygen. Okay. If they're every once in a while, you'll see one, the bigger atom, if it's in the same group, goes first. Okay, so if you saw SO, you'd go SO, but you don't see that very often. Greek prefixes are used to indicate each atom. You don't use mono on the first element. Okay, that's why I did carbon monoxide. You don't put monocarbon monoxide. But if there were 2, so if you had this, N2O, then it would be dinitrogen monoxide. Okay. So let me give you the Greek prefixes that you should memorize. I know there's a lot of memorizing in here, but that is just part of naming. So you'll see these 10. Mono, di, tri. Okay. Tetra is 4. Now these are a little easier. Penta, hexa, hepta, octa, nona, and deca. So these are these 10 Greek is capitalized, Greek prefixes. Okay. Now, let's go back to the rules. We talked about this. You don't use mono in the first. Give the name of the first element with its prefix, except mono if it's 1. Give the name of the second element with the prefix, okay? If the final A of the prefix is dropped, if you have oxygen, so like oxygen, you wouldn't say pentaoxide, you'd say pentoxide, but you would say dioxide, okay? But if the A is N dropped if you're dealing with oxygen. And then remove the ending of the second element and add I, just like the monatomic ions, which is a little confusing, but you just have to memorize that, okay? So, like I said, I've given you a couple, but if you had something like P4O6, that would be tetraphosphorus, okay? You don't change the name of the first element, and then it would be hex, and you drop the A, hexoxide. Okay, tetraphosphorus hexoxide. If you put hexoxide, I wouldn't mark it wrong, but I wouldn't want you to get laughed at outside of this class, so drop that A, all right? Okay, you can watch me do these all day long. You have to practice them. One more thing I'm going to tell you about naming, and it's some acid memorization that you're going to see in lab, and you should just know acids. We don't talk about acids and bases until the second semester, but a couple other things. These are just miscellaneous naming things. Acids. You should know these common acids. These are known and used in the lab all the time. This is hydrochloric acid. You've heard of that before. You should know it. This is nitric acid. Okay. This is sulfuric acid. And then this is acetic acid. And you'll learn later about strong and weak acids. These are strong acids. This is a weak acid. This is actually 5% solution of acetic acid is vinegar. And it's kind of weird that it's written that way, and we haven't talked about Lewis structures yet, but it's because this carbon has a double bond to it like that. And I'm putting the lone pairs in. Has hydrogens, and so you'll oftentimes see it written like that, so you know that, but you just know that it's actually a weird group like this. Okay, it's called the carboxylic acid group, and you learn that in organic chemistry. Okay. Now, one last thing, miscellaneous things, is you should know what are hydrates, and it's because a lot of ionic compounds will draw in water, because ionic compounds are these big lattices of ions. In fact, I'm going to pause the video and find a picture of one for you here in a second. But I want you to know that many ionic compounds absorb water when in the solid form. And they absorb a really specific number of water molecules, and so it changes the mass. So think of it, you've probably heard that term like something is X number of pounds when it's soaking wet. And that's because water has mass with it. And so you can, if I would ask you to name this compound, this is copper 2 sulfate. Okay, it's a transition metal. You don't know its charge, but you can figure it out because there's only one of them here, and there's one sulfate. And since sulfate's a -2, that means copper has to be +2. So that's copper 2 sulfate. And then you can actually buy copper 2 sulfate where it has 5 waters bonded to it. Okay, and that's just a little dot indicating a hydrate. And so when you calculate this, or when you name it and calculate the molar mass, the name of this is copper 2 sulfate, and then penta, because of 5, use your Greek prefixes, pentahydrate. Now, so these two things would have different molar masses because you just take copper, 1 sulfur, and 4 oxygens for copper 2 sulfate. In this case, you'd take copper, a sulfur, 4 oxygens, and then 5 water molecules. So you have to include the water in molar mass because it makes it heavier. That is one of the most important things you can learn about hydrates. And oftentimes people neglect these in general chemistry, but then you see them all the time. And so you have to make sure that you are aware that they exist. Okay, I'm going to stop the naming, and I want you to spend the rest of the day, the lecture time, making flashcards, practicing the 2 worksheets I'm going to put so that you can be proficient in naming. Oh, I'm going to quickly show you an ionic compound, and then I'll stop this video. So here's just a simple crystal structure of sodium chloride. The sodium's bigger and the chloride's smaller. So the purple's the sodium, the green's the chloride. And you can see they're arranged in this pretty lattice. And we'll learn more about this lattice structure later in the semester. But water can get stuck inside these lattices for ionic compounds, and that's where that concept of a hydrate comes from.